Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video and the next few videos are dedicated to solving trigonometric equations. These are actually some of the more challenging equations that you can face in mathematics, not because of their difficulty level, but because of what I've seen from students over the years. When they get into calculus and beyond, they end up forgetting how to solve trig equations, or they have a very loose understanding of what the solution of a trigonometric equation is or how to do it. So I'm dedicating this first video on the concepts behind solving trig equations because I really want it to be very clear as to why we do what we do when we solve trig equations. So let's go through this video, not solving anything, but talking about the tactics we would use and the reasons for those tactics and some things to watch out for. So first and foremost, you must be aware that you're finding reference angles when solving trigonometric equations. And a trig equation, by the way, is an equation that involves a trig function. So like sine of x equals 1/2. And when you solve an equation like that, you're not actually just finding one angle, you're actually finding an infinite number of them. And so you don't want to waste your time hunting down the all the values. Instead, all the values of angles that would satisfy this. Instead, you're looking for just a reference angle at first. You then use the sign of the trig function's value. In this case, the sign would be a positive. You would use that sign to tell yourself what quadrants your solutions are going to lie within. So for example, right down there, the sine of x equaling a positive 1/2. Well, we know sine is positive. Well, all trig functions are positive in quadrant 1. And then sine is positive in quadrant 2, and tangent in 3, and cosine in 4. Obviously, I also mean their reciprocals are also positive in the respective quadrants. So sine of x equaling 1/2 means that I have solutions that are either or both in quadrant 1 and quadrant 2. So I'll have two sets of solutions. One set dedicated to those emanating from quadrant 1, and one set of solutions from those that emanate from quadrant 2. So in this first example, what are the reference angle and quadrants for the solutions of the equation? Well, we know the quadrants are 1 and 2. So let's go ahead and just write that in here, quadrants 1 and 2. And then the reference angle. Now, you have to become kind of an expert at recognizing the very special trig ratios. Sine of x equaling 1/2. 1/2 is a special trig ratio. That comes from one of our special triangles. And that's what you're looking for almost the entire time when you're working with trig equations. You're really hoping to get those very special ratios. In this case, I always work in radians, by the way, so if you wonder why I continually write in radians, is because that's a habit that I have. If you write out your special triangle here, you'll see that the sine of pi over 6, opposite over hypotenuse, is 1/2. So my reference angle, x hat, is pi over 6. So again, trig is about those two things, reference angles and quadrants. So for this equation, which we have not solved at all, we know that the solutions are going to exist in quadrants 1 and 2, and they'll have reference angles of pi over 6. That's the only thing I'm asking so far. The next thing you need to be highly aware of is that trig equations have an infinite number of solutions. And this is something that I just mentioned a moment ago, but here we go. What value or values of x would solve sine of x equals 1/2? Well, we know, again, from the previous page, that the reference angle is pi over 6, and we have solutions in quadrants 1 and 2. Now, some students would say, therefore, x could be pi over 6, because that's a quadrant 1 angle with a reference angle of pi over 6. I'll write quadrant 1. And our quadrant 2 solution, some students would say, is 5 pi over 6, because again, that angle, 5 pi over 6, terminates in quadrant 2 and has a reference angle of a regular old pi over 6. Reference angles are so important. If you are weak at that, please study up, because it's very important. However, this is not actually the solution. It's close, don't get me wrong. So I don't want you to think that you all of a sudden don't know mathematics. You do. It's just that these are not the only solutions. Because if you take a look at, for example, 5 pi over 6, yeah, that's a solution, but so is 5 pi over 6 plus 2 pi. And so is 5 pi over 6, well, minus 2 pi. Or minus 4 pi. Or minus 6 pi. And so on and so forth. So we have to count all solutions, and the easiest way to do that is to say, well, I start at the regular positive x-axis, I move to pi over 6, so that's a solution, plus any rotation of 2 pi thereafter. So that is plus 2 pi k, where k is an element of the integers. That is, k could be 0, and if it is, then you could see if k is 0, we get pi over 6, or k could be 1, so it's pi over 6 plus 2 pi, or k could be 2, it's pi over 6 plus 2 sets of full rotations, or k could be 3 or 4 or negative 1. So we get to pi over 6 and we back off by a full rotation. No matter what, we still end at that same quadrant and same reference angle. So pi over 6 plus 2 pi k is the way you would write it for all the solutions that land in quadrant 1. Same thing for 5 pi over 6. It's 5 pi over 6 plus 2 pi k. So those are the values of x that would solve that equation. We have actually solved our first trig equation. It's a simple equation, but still, I don't want to take away from it. There's a lot of theory behind what we have done. The next thing I want to note, and you've just seen this, is that solutions to trig equations often use the quote-unquote rotational notation. I don't know any other way of calling it, but when I say rotational notation, I just mean the plus 2 pi k notation. And you have to kind of get used to that. And by the way, it won't always be plus 2 pi k. It might be plus pi k or plus 2 pi over 3k. We'll see that in future examples. Also note that in some textbooks, they use n instead of k. That's totally fine, as long as whatever parameter they're using stands for the set of integers or stands for numbers from the set of integers. This next piece is critical to understand. The solution to a trigonometric equation is always an angle. And that is very important to understand because you're solving things like cosine of theta is equal to some number. You want to, well, maybe I should actually put in a number, 1/7 or something like that. You want to find out what that angle theta is. It's very, very important that you understand that that's an angle. Also, intimate knowledge of the special ratios is very important. These are the ratios that are born from our special triangles, right? So pi over 6, pi over 3 right angle, and then our ratios are 1, 2, and a root 3, or you could have your 45, 45, 90, or in my case, as I write in our radian measure, pi over 4 right angle, and those ratios are 1, 1, root 2. And the other thing you'll have to be very aware of is the graphs of the sine and the cosine functions. The reason why that's necessary is because you often are dealing with equations that instead don't equal, let's say, 1/2 or root 3 over 2 or 1 over root 2 or something like that, but instead are 1 or -1 or something like that. Those are quadrantal angles that lead to those values for the sine and the cosine. And so to know very quickly what the cosine graph looks like, this is the graph that y equals cosine of x right here. To understand very quickly what that looks like allows you to quickly find out what value of input leads to an output of -1. So in this case, pi, an input of pi, and then of course plus 2 pi k, because every rotation of 2 pi thereafter will get you to the value of -1 for the cosine. So knowing the graphs of the sine and the cosine, very important for you to help you solve trig equations. If you need to review that material, please go back in my YouTube video series to watch the graphs or the video on graphing sines and cosines. The next piece of information that's very important is that trig equations often require solution techniques from algebra. That is stuff like factoring, right? Factoring out greatest common factors. Every once in a while you have to use the quadratic formula. So basically knowing how to solve algebraic equations is going to help you in solving trig equations. So if you have a shaky foundation of algebra, it's really going to hurt you in trigonometry. And that's why algebra is a prerequisite for a trig course. And just like algebraic equations can involve mixtures of different functions, trig equations can involve mixtures of different trig functions. And what I mean by algebraic equations can involve mixtures of different functions, I mean, you can have an algebraic equation that's like e to the x plus square root of x minus the natural log of x is equal to 4. That is a terrible equation. You would not be able to solve that by hand until you get to Calc 1. And in Calc 1, you can approximate the solution of that using something called Newton's method. But in our courses in algebra, you normally can't even approach a solution to that equation. But in trig, you can have a mixture of trig equations. So let's say you have an equation that looks like this: sine of x plus, let's say, I don't care. Let's say it's the tangent of x is equal to cosecant of x or something like that. That's a mixture of trig functions. And in this case, you would have to kind of invent a way to make this work. In fact, this would work better if that was a cotangent, to be very honest with you. So this could be solved, but you have to be willing to look for a way to solve that. You need to get them all to be either the same trig function or be able to factor out a trig function. So how do you do this? If given an equation involving different trig functions, some tactics include, but are not limited to, the following. 1. Set the equation to 0 and factor so that each factor has a unique trig function. Now, what do I mean by that? I mean this. If you have something like, let's say, a sine of x plus a sine of x times a cosine of x is equal to, I don't care really, let's just say it's equal to 0. Okay. Note, because it has to be equal to 0 for this first tactic, note that the first two terms, or the two terms on the left-hand side, both have a sign. So you could factor out that sine of x, and you're left with a 1 plus a cosine of x is equal to 0. Well, now you can use, from algebra, the zero factor principle, which tells you that if you have a product of two objects, sine in this other picture, and it becomes 0, then one of those factors must be 0. I'm having a hard time talking today. So that means that either sine of x is equal to 0, or 1 plus the cosine of x is equal to 0. So that's one tactic. It only works if you can factor out a common trig function out of your statement. If you can do that, then good for you. Where it's not going to work is if it was something like this: sine of x plus sine of x times cosine of x, which so far looks like it's going to work, is equal to 1. Now we're in trouble because we know from algebra that while you could possibly factor this out just because you can, this does not imply that sine of x is equal to 1 or 1 plus the cosine of x is equal to 1. This does not mean that. Because just because two numbers multiply to become 1, it doesn't mean that one of the numbers has to be 1. One of the numbers could have been 2 and the other one could be 1/2. So we cannot use that little property of setting each factor equal to the right hand side. You can't use that unless that right hand side is 0. So to do this needs to be 0. Needs to be 0. So that's a kind of a warning. Let's see. 2, another tactic. Use trig identities to rewrite the equation in terms of a single trig function. Often you're looking for Pythagorean identities, double angle identities, or half angle identities. So an example of this, and I'm kind of just making this up, but an example of this would be something like, let's say you have a cosine squared of x minus sine of x plus 1 is equal to 0 or something like that. Actually, let's make that a minus 1. It's better if it is. So in this case, that's a mixture of trig functions. That's like somebody saying, hey, solve y squared minus x minus 1 is equal to 0. You just can't do that. You can't find out what x is. But in this case, we have a trig identity that allows us to trade out that cosine squared and turn it into a sine squared. So that cosine squared can be rewritten as a 1 minus sine squared. And then we still have the remaining minus sine of x minus 1 is equal to 0. And in this case, you can see the 1 minus 1's cancel. I'll multiply both sides by a negative 1. You get sine squared of x plus sine of x is equal to 0. Technically, here I could just factor. But just to let you know, you want to look for those types of identities. The Pythagorean identities, double angle identities, half angle identities, sum and difference identities actually do help out as well. Not very often, but they do help out. So look for trig identities. That can be very helpful. It is a trig course, right? Finally, and again, this is not an exhaustive list. It's just the top 3 that I can think of. If the equation involves a secant, a cosecant, or a cotangent, multiplying by the cosine or sine or tangent, respectively, can help at times. So that brings us back to that top one I wrote out there. That's a sine plus cotangent plus cosecant. So let me write that, or it's not plus cosecant, but whatever. So it's a sine of x plus cotangent of x is equal to the cosecant. Let's just pretend you were handed that. That is a really terrible mixture of trig functions. However, I know that the denominator of both of these guys right here is a sine function. So I'm going to multiply both sides by the sine. If I multiply both sides by the sine, I will get right here a sine squared plus, well, cotangent is cosine over sine. If you multiply that by sine, the sines will cancel. So you get plus a cosine of x is equal to, and cosecant is 1 over sine. If you multiply it by sine, you get a 1. And you look at that and you say, but that's still a mixture of trig functions. And it is. However, I have a trig identity I can use. Sine squared is 1 minus the cosine squared. And then we still have plus cosine. And we have that equaling 1. And then you can subtract 1 from both sides and, do the rest of it. So the idea here is really to eventually get down to either one trig function in your equation, like sines for number 2 or cosines for number 3 there, or be able to factor out trig functions to set things equal to 0 and then factor out trig functions so each factor has their own unique trig function. Those are good tactics right there. All right, so one last piece of advice. And this one's more of a difference than a piece of advice, but Unlike algebraic equations, so the last example I threw up there was that, like algebraic equations, you can have a mixture of trig functions within your equation. But unlike algebraic equations, even if you have the same trig functions, there could be a complication of them having different angles. That is, you could be given sine of 2x plus sine of x is equal to 1 or something like that. This is, you can't do anything with this as written because these angles are different. The arguments of the sine functions are different. So you can't just say, I'm going to factor out a sine. It doesn't work. You have to get them all to have the same angle or arguments. Luckily, we have a double angle identity that tells us that sine of 2x is the same as 2 times the sine of x times the cosine of x. And then we have this plus sine of x. And of course, I said that's equal to 1, which means I can't really solve this because, unfortunately, I can't factor if I set things equal to 0. So in other words, if I subtract 1 from both sides, I can't factor that. I can't factor a sine out of each of those terms. So this one's kind of locked. I made up an example that's locked. It would have been better if I said equals 0 there, then it would have worked out. But anyhow, the idea is to get all of your arguments to be the same as well. So if the arguments are x versus 2x, get everything in terms of x rather than 2x's. Use double angle identities and sum and difference identities. Those can be very, very helpful. And I'll showcase those as we go through examples. But that's all my advice, at least to start with. We will go through basic examples first, basic equations, and then grow from there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.